Welcome to this video on solving absolute value inequalities. We're going to look at two examples. Here's the first one. Suppose we're trying to find all values of x for which this statement is true. In other words, suppose we're trying to solve this inequality with an absolute value in it. Well, it turns out, like most inequalities, there are infinitely many x's that make this true. But there are also infinitely many x values that would make this false. And it's our job to sort out the truths from the falses and ultimately report back what is the totality of all the x values that make this true. So to embark upon that, one strategy is to turn the inequality into an equation. Because it turns out that the solutions to this equation on the right side will be the dividing lines between the true and false sections, or the true and false intervals, for the inequality on the left. If that's a little vague, I'll show you what I mean. First, let's solve the the equation on the right. I'm going to do the basic steps. I'm going to isolate the absolute value, split the equation, and then solve each one. You may want to hit pause here to analyze the work. If you don't know how to solve absolute value equations like the one you've seen there, or if it's been a while since you've learned it, you may want to watch that video first called Absolute Value Equations. But remember, we're not solving an equation here, we're solving the inequality on the left. So what do 8 and 2 tell us? Well, they tell us that the numbers 2 and 8 are the dividing lines between the true and false regions of the number line in relation to the original inequality on the left. So what that allows us to do is to solve the inequality on the left using the equation solutions on the right. Here's how you go about that. Notice that these two solutions break the number line up into 3 separate intervals. We're going to go one by one through the intervals and decide if the numbers in each interval are a solution. For example, let's look at the interval from -infinity through 2. Now what I've done here, you may see it in red. I've picked a somewhat arbitrary number, just any old number in that region. 0 is to the left of 2, so it seemed like a good enough number to try. Now my plan here is to plug in 0 for x. And before I do that, here's the overall strategy. If 0 turns out to be a solution to the original inequality, then so will every number in the open interval from -infinity to 2 be a solution. Or reversely, if 0 turns out not to be a solution to the original inequality, then neither will any number in that interval. So let's test that. Notice I've substituted 0 for x. Now I use scratch paper to work out the expression on the left side, and I didn't show my work here, but the entire left side worked out to 11. Notice 11 greater than 7 is a true statement. 11 is greater than 7, and that indicates that 0 is a solution to our inequality. But we're not interested only in knowing the fact that 0 works. We're interested in what that implies. And the fact that 0 works implies that everything in that whole interval, from -infinity through 2, works. So I've now found part, or maybe all, of my solution. But to know for sure, I'm going to have to test the second and third interval on this number line. So I've chosen a somewhat arbitrary number here, 6. 6 is in the interval from 2 through 8. There's nothing special about 6, it's between 2 and 8, so I picked a random number between 2 and 8, and I'm plugging that into the original inequality. Now I worked this out on scratch paper, and I didn't show it in this video, but the left side does in fact work out to 3. What does that tell us? Well, 3 greater than 7 is a false statement. That means that x equals 6 is not a solution to our inequality. But because it's between 2 and 8, the solutions to the corresponding equation, I've just shown not only that 6 isn't a solution, but that there are no solutions between 2 and 8. So no need to try anything else. That entire middle interval has no solutions in it. And now let's try the third interval. I've chosen 10 here. You don't have to choose 10. You can choose 11 or 13 or a million. All those numbers are between 8 and infinity. So I've chosen a number between 8 and infinity. And I'm plugging that in. Now again, I did my work on scratch paper, but the left side works out to 11. And 11 greater than 7 is in fact a true statement. Well, what does that mean? That means that 10 is a solution. But if 10 is a solution, we can conclude that so is every number 8 through infinity. And so I can say with certitude that all numbers between 8 and infinity are solutions to this problem as well. So what have I deduced so far? We're not quite done yet. Going from left to right here on our number line, we've deduced that every number between negative infinity and 2 is a solution. And we've deduced that every number from 8 through infinity is a solution. But there's one issue that and we also concluded that there are no solutions between 2 and 8. But there's something we haven't addressed yet. And that's the question of the endpoints of these intervals themselves. In other words, let's start by asking, is 2 a solution to the inequality? We know it's a solution to the equation, but is it a solution to the inequality? Because if it is, then we have to include it. Notice the bracket of inclusion here. Okay, well, one way to find out, substitute 2 for x. Once again, scratch paper not shown, the left side works out to 7. 7 greater than 7 is a false statement. A number can't be greater than itself. And since that's a false statement, we know that 2 is not a solution to this problem. And if 2 is not a solution to this problem, then I can't include it. The last unresolved issue is x equals 8. Is x equals 8 a solution to this problem? Well, if it is, then I'll have to include it in my interval using the bracket of inclusion. Plugging in 8 to the problem and doing the scratch work, not shown here, gives me a false statement. 7 greater than 7 is false, therefore 8 is not a solution, and therefore I can't include it in my answer. So after all this testing of different numbers and endpoints, I've now deduced that all numbers from negative infinity through 2 are solutions, as are all numbers from 8 through infinity. So we write that using the union symbol between the two intervals. The union symbol is not a capital U, although it looks like it, and it is inspired by that. The union symbol is technically the mathematical symbol for or. But in a more practical sense, we use the union symbol to join two intervals together into one set when those two intervals don't touch. In other words, the interval from negative infinity to 2 and the interval from 8 to infinity don't overlap. And so by putting a union symbol between them, we're consolidating those two separate intervals into one answer. Here's our second of two examples. Let's apply the same strategy here. Again, there are going to turn out to be infinitely many values of x for which this is a true statement. But there are also infinitely many values of x for which it is a false statement. I'm therefore trying to parse those out and find out which x's make it true ultimately. Well, because I have an inequality, one strategy you can use is turn it into an equation. And now I can just use my solving skills to solve that equation on the right side of the screen. I can subtract 3 from both sides, Then I could divide by -2. And now that the absolute value is isolated, I can split it into two equations and solve each one separately. Now, those two numbers are not necessarily solutions to the problem, and even if they are, they're not all of them. What do those two numbers mean? What does it mean to have solved the equation? What that means is, on a number line, while those numbers may or may not be solutions themselves, they are the potential dividing points between true regions and false regions in relation to the inequality that I'm trying to solve. So I'm going to once again notice that there's three intervals on the number line separated by these 2 points, and I'm going to test out each one of those intervals by picking random numbers. Here's a random number. -13 is in the interval from -infinity through -10. So notice I've substituted -13 for x. Scratch work not shown. This thing turns out to be a false statement. And that means that -13 is not a solution to this inequality. Now, -13 was a somewhat random choice of numbers in that interval, but it tells us more than just that -13 isn't a solution. We now know that there are no solutions to this inequality between -infinity and -10. Testing out the next interval, let's choose the number 1. 1 is definitely a number between -10 and 2, and I'm going to plug that in. Notice I've substituted 1 for x. And when I do my scratch work, the left side works out to be -7. Now notice this is a true statement. -7 is greater than -9. But that tells me more than just that 1 is a solution. I mean, I've just shown that x equals 1 is a solution to the inequality, but I know more than that. Because 1 is on the interval from -10 through 2, it must be true that all numbers in the interval -10 through 2 are solutions to this inequality. So I've just found infinitely many solutions, all the numbers from -10, between -10 and 2. But I haven't finished analyzing the number line yet. Let's now analyze the interval from 2 through infinity by picking a random number there. Plugging 6 is just an arbitrary choice there, plugging 6 into the inequality, doing the scratch work, not shown here, gives me a false statement. -17 is not greater than -9, and it's certainly not equal. And so, because that's a false statement, I know that x equals 6 is not a solution to my inequality. But because of the nature of solving the equation and using those two numbers as boundaries, I not only know now that 6 is not a solution, I know that there are no solutions between 2 and infinity. Now, I'm not done yet, but let's summarize what we've done so far. Going from left to right on the number line, we've deduced that there are no solutions between -infinity and -10, that every number between -10 and 2 is a solution, and that there are no solutions between 2 and infinity. But once again, that leaves a couple of unchecked items. First of which is the question of whether -10 itself is a solution. Plugging, well, if it is a solution, then we're going to have to include it. Notice the bracket of inclusion there. If it's not, then we won't. So plugging -10 in for x. Once again, scratch work not shown, but the point is, I have a true statement there. -9 is equal to -9. So we've just shown that -10 is a solution and therefore needs to be included. And if -10 has to be included, then I'll leave the bracket there to indicate that. But I'm not done because I still haven't figured out whether 2 is a solution. If 2 is a solution, I'll have to include that as well with a bracket there. Let's find out. Plugging 2 into the inequality, you can check the scratch work yourself. It does work out to be a true statement. -9 is equal to -9. And because that's a true statement, then 2 is a solution. And because 2 is a solution, I have to include it as well, leading me to my final answer shown here, the closed interval from -10 through 2. That concludes this lesson. Thank you so much for watching.